In this lesson, we are going to analyze function graphs to determine our x and y intercepts, values of the function, and a quick review of domain and range. So an investor assessed the average daily value of a share of a certain stock over a 20-day period. The value of the stock can be approximated by the function you see on your screen. Notice that this would be a quartic function, degree 4. And my domain right here, I would call this my relevant domain for the model, is restricted between 0 and 20 days. Can't go back in time, and this is of course over a 20-day period, so this would be our relevant domain for the model. Part A, we're asked to use the graph to estimate the value of the stock on the 10th day. Confirm your answer algebraically. So for the 10th day, I'm going to move up to my curve. And I would say that this is hitting at about 31, maybe 32. So I'm going to guess approximately 32 days. Now, to determine this algebraically, I'm simply going to substitute 10 everywhere there is a D. And when I substitute in, I do confirm that V of 10 is equal to 32 days when I compute this algebraically. Secondly, we're asked to use the graph to estimate the days during which the stock was valued at $30 per share. Confirm your estimate algebraically. Well, so this is saying when is my y value equal to 30? So right here, here, and here. So I'm saying that at day 0, between day 9 and 10, and then it looks like between day 15 and 16, it is equal to $30 per share. Now to confirm this algebraically, plugging 30 in for our y would cause us to have to solve a quartic function. And at this point, we're not going to do that. So just algebraically would be to confirm if you plugged in 9 into your function v of 9, and then you plug in v of 10, I think you'll confirm that $30 per share falls between the two. So v of 9 ends up being 29.902, and day 10, the value of the stock is $32. So it happens between the 9th and the 10th day, and you would do the same process for between the 15th and 16th day. Now, if you look back at day 0, I actually know that that's not quite right. When you look at the graph, it looks like it, but if I plug in 0 into my function, I'm going to be left with 31. So it really only happens between the 9th and 10th day and between the 15th and 16th day. When we're analyzing our functions, we can never forget domain and range, so just a little more practice here. The domain of the first one, how far left, how far right, so it begins at -8. Looks like I have a hole right here I need to watch out for, and it goes infinitely to the right. So I am going to say bracket -8 to -4, union, because -4 is not part of the domain, to positive infinity, and you can't bound infinity, so it gets a parentheses. The range, how low does this go? Looks like it goes as low as -10. And then how high does it go? Well, it goes up. There is a hole here, but it's compensated right here where it's closed in, and it goes infinitely up. So my range is -10 to infinity. Okay. On the right, practice and check your work since you've seen this before. And you can see my answer on the screen. Let's look at some important vocabulary now for this curve. The point at which the curve crosses the y-axis is, of course, known as the y-intercept. When finding a y-intercept, you think about, okay, so it is always in the form of 0, y. So how do you find it? You do f of 0. You plug in 0 and you get your y-intercept. Now, the places where it crosses the x-axis, yes, is known as your x-intercepts. So notice that you can have multiple x-intercepts. It's possible you'll have 0 places where it crosses the x-axis. You could have 0, you could have 1, you could have 2, you could have more than that depending on the degree of the function. But if it's really a function, you will only ever have one y-intercept. Okay, The x-intercepts are often called the zeros of the function as well. It says use the graph of each function f to approximate its y-intercept, then find it algebraically. So as I look at where does this cross the y-axis, I'm going to guess that my y-intercept is something like 0, 1.25, at a quick glance. But then to actually find it algebraically, I'm going to plug in f of 0. And when I do that, I'm going to be left with the 4/3, because if this is 0 right here, that's gone, and I just have 4/3 remaining. So my y-intercept is 0, 4/3. On the second one, the y-intercept, as I'm estimating, appears to be about 1, 2, 3, 4, approximately 4. And then algebraically, if I do g of 0, that gives me the absolute value of -5, which is 5 minus 1 is indeed 4 for my y-intercept. You'll see it written just like this. You'll also see it written as an ordered pair. Now, to find the zeros of a function, so again, the x-intercepts of the graph of the function f are also called zeros. Okay, so these are synonymous terms. But the solutions of the corresponding equations, so when we're talking about the solutions, these are also referred to as the roots. And to find the zeros of the function, again, the zeros where it crosses your x-axis, this would be some point, comma 0. So we're letting the y be equal to 0. So to find the zeros of the function, set f of x equal to 0, then solve. So this says use the graph to estimate the zeros and then find them algebraically. So in the first one, notice that this is counting by 2's. So I would say that my x-intercepts, x is approximately maybe -2.5 and positive 2.1. Okay, now that's definitely a guess. What I'm going to need to do here is set my function equal to 0. So I would have 2x squared plus x minus 15 is equal to 0, and this is just a quadratic function. So to solve it, you've got several methods. You could try to factor. If factoring is not what you're quickest at, you could always do quadratic formula. Let's see, this factors into 2x minus 5 and x plus 3. Check your outer and inner product just to make sure. And then I solve each of these using the zero product property. So 2x minus 5 equals 0, or x plus 3 equals 0. So my solution here would be x equals 5/2, or x equals -3. So those are my zeros of my function, or my x-intercepts. So it's pretty close with the one, the other one definitely off. All right, part B looks like a radical function. So we need to estimate, looks to me like it's my 0 is approximately -1/4, guessing a little bit here. And I'm going to solve this algebraically. So I set my function equal to 0, and I start solving this. So if I square both sides, that gives me 0 equals 4t plus 1, and then I solve for t. Gives me -1 equals 4t, or divide and I get t equals -1/4. So not a bad estimate. So my t-intercept, or my x-intercept, is -1/4. This final one is a cubic function, and notice that there are 3 zeros. So estimating, I'm going to say approximately 0, probably 1.3, and it looks like 2 exactly. So to solve this, I again set my cubic function equal to 0. And to solve this cubic function, I'm going to use my factoring methods. I'm going to begin by factoring out my GCF, which is x. So that produces x times the quantity of 3x squared minus 10x plus 8. And then I'm going to attempt to factor this again. Quick reminder for those of you who use the tic-tac-toe method to factor, I'll do 3x and x gives me 3x squared. Factors of 8 could be 8 and 1, 2 and 4. I know they're both going to need to be negative because it needs to be a positive. That sums to a middle term that's negative. So I'm going to try, let's see, probably the 4 and the 2. I'm going to put the 2 here and the 4 here, multiply across, gives me negative 6x. Negative 4x, I sum, and yay, it adds to negative 10x. So my one factor is x minus 2, and my second factor is 3x minus 4. Now I apply the zero product property, and I get x equals 0, 2, or 4/3 for my algebraic 3 zeros of my function.